So in the previous lecture, we talked about yaoi and its many implications and stuff, like how its female counterpart yaoi, and it's all part of a general genre. Boys love, girls love. So today's lecture, I'm gonna be integrating quantum mechanics into the study lecture. So we're gonna integrate quantum mechanics into the study so that we can model trap behavior. So I hope you guys learned a little bit of linear algebra or quantum mechanics itself, and also Broncat notation, Dirac notation, in order to understand the notation used in this video. So to begin, I want to first say that the traps that we're gonna be modeling here, or femboys, are idealized. It's gonna be like high school physics where we ignore air resistance or friction. But in this case, we're gonna be thinking these guys, or these traps, as subatomic particles or quanta. When I say quanta, it's basically light waves, photons that act as a wavelength that cause disturbances that we perceive as visible light, or electromagnetic light, or waves, basically. And so, femboys are going to be treated as quanta or subatomic particles, such as quarks, leptons, gluons, etc. So, the first thing I want to discuss are states, rather gender states. And they're denoted by a ket vector. And a ket vector is just basically any vector. It's going to be A, B, dot, dot, dot. That's a ket vector. Now, what is this symbol over here? This symbol denotes psi over here, the Greek letter psi, small letter psi, or yes, psi, denotes what is known as the wave function. And what is a wave function? A wave function is a complex value function that gives us the probabilities of the position, momentum, velocity, etc., you name it, of the subatomic particles or quanta. So it gives us the probability. We cannot precisely measure the momentum, position, or the velocity, whatever you name it, of subatomic particle or quanta at a specific time. We cannot do that. But we can draw probabilities on the position, momentum, etc., you name it, of the subatomic particles or quanta. We'll do the same thing when it comes to traps and predicting their decisions and their behavior. Most notably, their gender and their appearance. We'll focus on these two things. We're not going to focus on sexual orientation because I want to exclude it for now, because femboys can be any sexuality, and it wouldn't matter. They can have a sexuality of 0 while their gender states are different. So when we say a quantum state, everyone thinks that the word quantum is just some fancy science term that scientists attaches to things to make it sound very fancy. But in fact, quantum just means very small. That's why we say quantum mechanics, because quantum means very small in mechanics. We're describing the mechanics of quantum objects, or objects that are smaller than an atom. Very small things, basically. And so, alright, so quantum states. Quantum states are denoted by a ket vector plus a wave function. And the wave function can be characterized as a sub x times e to the I 2 pi f sub x t plus v phi sub x. And this is some function that gives us a wave type thing, or a decaying wave type thing. And the reason why I'm saying that is because e to the I, this expression, just basically equals the cis function of this thing here. And the cis function is denoted by cosine of cis function of theta is cosine theta plus I sine theta. And we just take this expression over here to be theta, and then we get cosine of 2 pi f sub x t plus phi x plus I sine 2 pi fx t plus phi x. And as you notice, cosine and sine are waves, or they are functions that describe waves, which is why we call this the wave function. And not only these waves do not predict, these waves do not describe the position, momentum, velocity of a given subatomic particle or quanta, but rather they describe the probability of its momentum, position, or whatever of the subatomic particle or quanta at a given time. So how likely they are in this position, how likely they are in that position, how likely did they take this path, how likely did they take that path, are described all within this function. And ax, f of x, and phi sub x are all constants that are determined by initial conditions that are given to us. Initial conditions are just basically as it states, the condition of the system that we want to describe, or the subatomic particle quanta. So, in quantum mechanics, there are 4 main quantum states. Well, actually just 2 main quantum states, or actually 2 main states, not quantum states. Those states are the spin up, spin down, spin left, and spin right. And these guys are described via ket vectors again. And I'm going to tell you guys again that a ket vector is basically just a vector, just a rectangular array of numbers, and this can be described as an arrow in space. It's just neatly described as a rectangular array of numbers. And the reason why we use ket vector notation or Dirac notation over here is to simplify things. So moving on, we want to be concerned with. We are concerned with 4 main states, and that is the male state, the female state, the masculine state, and the feminine state. These 4 main states are what we're going to focus on, and if we use these guys and plug them into our wave equation, or this over here, I'm going to use a different marker. This wave equation over here, the thing that I wrote a while ago, is actually equivalent to alpha times the spin up state plus beta times the spin side state or spin right state. These are actually indicative of the basis vectors of a system, which is I hat and j hat. This is basically just j hat, this is I hat, but but apparently we just need to use the Dirac notation, so that's that. And these identity vectors are, we want to transform these into these guys. So if we were to do this, it'd be male and female, or actually male and the masculine, perhaps, base vectors. But I want to implement all of these guys so that we can maximize the potential of this system over here. So if we input all of these and use all of these guys, we get what I'd like to call the trap certainty equation. And the trap certainty function, trap certainty function, or rather trap certainty vector function, is this time we're not modeling probabilities of the particle itself, but we're modeling our certainty of the experiment at certain time intervals. So this is characterized by alpha times the male state plus beta times the female state plus theta times acting on the masculine state plus omega acting on the feminine state. And all these alpha, beta, theta, and omega are complex value functions. So I'll just write that. Beta, theta, and omega, element of complex. So what about this now? What do we do with these guys next? Now, since we know these guys are our basis vectors, now let's think, speaking of vectors, let's think about or talk about the eigenvector eigenvalue equation. This equation pops up a lot in quantum mechanics, in linear algebra, and a lot of people are very confused as to what it is. So basically, the eigenvector eigenvalue equation is basically given a matrix A and a eigenvalue lambda, which is determined from A, this vector. So basically, the matrix acting on a vector is equal to lambda acting on the same vector. And what we mean by this vector over here, what is this vector over here? What is V in this equation? V is basically a vector that doesn't change or get knocked off its span when we do that, when we apply that A transformation on the grid. So when we start to think of A as a transformation on the basis vectors of a system like I had and J had, then we quickly get a good glimpse of what exactly A is. And so the eigenvalue equation in quantum mechanics is H hat times a certain state alpha equals lambda alpha, and this times acting on the same state. And this H over here is called a Hermitian matrix. And what is a Hermitian matrix? It's a matrix, a rectangular array of numbers that contains complex valued things. So it can be like 1 minus I, 0, 0, 1 minus I. This is a Hermitian matrix because it contains complex numbers in itself, like I, where I is the imaginary unit square root of -1, but we treat it as a legitimate number, but that's something for another day. So if we think of this as transformations, we can think of this guy or formulate it as an experiment that we're doing on the trap or the femboy. So if this is the state of the femboy after the experiment, this is the experiment. This is some arbitrary value we find from this. And so it's acting on that. So once this acts on the system, once we apply the experiment on the basis vectors or the configuration of our femboy, this is his state after the experiment. And this is some arbitrary value like energy. Now if we actually take this to be not a Hermitian matrix but a Hamiltonian operator, and if we input our trap certainty function in here and take this to be the energy, this actually collapses into Schrodinger's equation, or generalized form of Schrodinger's equation, which is H bar times a certain wave function, vector wave function, is equal to the energy times that wave function. And I'll talk about the energy in a while, but H hat is equivalent to negative H bar squared over 2m, the mass of the particle, times nabla squared, plus some weight function, v of RT. And we know that our wave function here is actually a function of t, so this makes sense, and r is just some other concept. But if our function here is two-dimensional, but if it's one-dimensional, it just degrades to v of t. And so if we plug that into here, we get negative h bar squared over 2m times nabla squared of our state equals our wave function plus v of t times our wave function equals e times the wave function. All right. This is Schrodinger's time-dependent equation, or the time-dependent Schrodinger equation. Very important equation in quantum mechanics. It governs the velocities and momentum of subatomic particle in quanta, and thus will be used in governing the behavior or our certainty of our experiment on the trap or femboy. And what is h bar? H bar is basically just h over 2 pi, where h is Planck's constant. Planck's constant. Named after Max Planck. I'm not really gonna discuss much about h, but that's what h bar is. H bar is h over 2 pi. That's what it is. And so from here, alright, so here's when the idealization comes in hand. So I'm gonna write the Schrodinger equation on the other side, and we're gonna let's assume or use the time-independent Schrodinger equation, which just tells us to find the derivative of it. So we're just finding the second derivative with respect to x, or with x. And this time our wave function or certainty function is a function of x alone. So it simplifies that nabla is basically telling us to find the derivatives of the function. And so we're just simplifying that. So it becomes negative h bar squared over 2m times d squared of our state over dx squared, and minus our state times the weight function equals energy times the weight function. And I'll continue this in the next part.